So last time was all about a single chirality center, a single asymmetric carbon. What if you have more than one asymmetric carbon? There's a formula presented here that says the maximum number of stereoisomers is 2 to the n, where n is equal to the number of stereocenters. Remember, stereocenters and asymmetric carbons are similar but different. That Venn diagram, don't forget that fried egg. Well, let's walk through an example of what to do with molecules that have more than one asymmetric carbon. For the compound, 2-bromo, 3-chloro-butane. So that's 2-bromo, 3-chloro-butane. How many stereoisomers are there? Draw them all, give the relationship of each pair. Before we even get started on any of that, we need to identify how many stereocenters, how many asymmetric carbons do we have. We don't have any stereocenters that are not asymmetric carbons because I don't have double bonds, I don't have rings. But this carbon and that carbon are both asymmetric because this carbon has a Br, an H, a methyl, and a carbon that's not a methyl. Let's just say it that way. This other carbon has a Cl, an H, a methyl, and you guessed it, a carbon that's not a methyl. A CH with a Br with a CH3, yeah. Those branches are different. So we have 2 asymmetric carbons on this guy. So 2 asymmetric carbons means 2 to the 2, 4 possible stereoisomers. Note that's possible. We're going to talk about that. How do I draw all of these? I'm going to draw 4 little templates where my zigzag is in the same orientation. I'm going to point my Br up and my Cl down in each of them as far as like this. I'm not doing dashes and wedges yet. But I'm going to make each of them start out looking like my blue structure up there. Then I go through and do all dash wedge combinations. Wedge my Br. Wedge my Br. Dash my Br. Dash my Br. Wedge my chlorine. Wedge my chlorine. Dash my chlorine. Dash my chlorine. Yeah? Okay, then what? It says give the relationship of each pair. So I'm going to give these guys letters so that we can give the relationship of each lettered pair. That means A and B, A and C, A and D, B and C, B and D, and C and D. A lot of pairs. I didn't plan well space-wise. I'm going to start with the thing or things I'm most confident about. What are enantiomers? Enantiomers are non-superimposable mirror images. Enantiomers have this opposite absolute configuration at every chirality center. They are non-superimposable mirror images that have the opposite configuration at every chirality center. So, do any of these look like mirror images that are non-superimposable? To me they do. A and D are enantiomers. What if you're not as confident as I was about that? How can you hedge your bets? One way is you could assign R's and S's, absolute configurations, to check behind yourself. So if I imagine an H over here on my BR, and I assign priorities, hopefully you know the rules, I assign priorities around that BR stereocenter. 1 to 2 to 3, lowest priority in the back. This BR stereocenter is an R stereocenter. If I assign priorities around the chlorine stereocenter, hopefully you know the rules. We got to include the hydrogen back there, number 4. 1 to 2 to 3, lowest priority in the back. This is an R stereocenter also. While I still have the blue pen, let me double check over here. My hydrogen would be wedged. My priorities are as follows. 1 to 2 to 3 looks clockwise, but my lowest priority is coming toward me. It's the opposite of what I expect. So 1 to 2 to 3 looks like R. This is really S. And back to bromine. We got to consider that wedged hydrogen. 1, 2, 3, 4. 1 to 2 to 3. Lowest priority is in front. 1 to 2 to 3. Clockwise looks the opposite, really counterclockwise. S. So A was the R enantiomer. D is the S enantiomer. They are enantiomers. Because I went to the trouble of assigning those two molecules, A and D, I can take advantage of recognizing which groups are similar and going ahead and assigning R and S based on appearance without picking out priorities and doing rotational stuff. Meaning, this first carbon has bromine as a wedged, methyl down, ethyl down, bromine as a wedge. This looks identical to that. Like the setup of around this bromine center is identical. So that means that this is also an R stereocenter. On molecule B, the chlorine part looks like molecule D's chlorine part. That means that's an S. Molecule C, super easy. Bromine matches the bromine in D, that means it's S. Chlorine matches the chlorine in A, that means it's R. You can verify that 100% with assigning priorities, double checking, lowest priority back, clockwise is R, etc., etc. But we can also take a shortcut when we know the rules. So I may have been able to, prior to now, recognize that B and C are the opposite at both configurations. They are also enantiomers. I have two pairs of enantiomers here, and that's all. What about something like the RR compared to the RS? Those are not enantiomers. Enantiomers have to be the opposite at all asymmetric carbons. If you're the same at some, like this, and opposite at others, like this, that pattern is called diastereomers. Yep, that's great. Diastereomers are compounds that are non-superimposable images as well, but they're not mirror images. They're stereoisomers that are not mirror images. So A and B has one the same, one different diastereomer. A and C, one the same, one different diastereomer. B and D, one the same, one different diastereomer. And you guessed it, C and D, one the same, one different diastereomer. Diastereomers are stereoisomers that are not mirror images. If you're talking about asymmetric carbons, diastereomers has to have at least one asymmetric carbon the same and at least one asymmetric carbon different. Okay, I think I got it. Let's try another example. 2,3-dichlorobutane. I'm going to do the same thing I just did. ClCl, how many asymmetric carbons? 2 asymmetric carbons, therefore 4 possible stereoisomers. So I do my same combos as before. Wedge, wedge, dash, dash, wedge, dash, dash, wedge. And I feel super confident, and I run down the list and I say, A and B are enantiomers, and C and D are enantiomers. And I say, whoop, hold up, that's not right. What? They look the same as those last examples we just did. I drew them in a different order, not really on purpose, but oh well, we're rolling with it. A and B are enantiomers. I agree. C and D are not enantiomers. C and D are identical molecules. So if your job was to draw all stereoisomers of 2,3-dichlorobutane, you should not draw both C and D because those are identical. You need to recognize that they're the same and therefore not draw one of them. Wait, what? I thought I got this. I know, it's confusing. Hold on. Compound C is what's known as a meso compound. A meso compound is a compound that definitely has more than one chirality center, more than one asymmetric carbon. You cannot be meso if you only have one asymmetric carbon. So in one of its conformations, this meso compound, in one of its conformations, there will be a plane of symmetry. Let's show you what that plane of symmetry looks like in this molecule. The plane of symmetry is not easy to see in this orientation, but if I rotate that molecule, I'm going to rotate it like this. I'm going to rotate around that central bond to where my methyl that's in the plane now comes 180 degrees and is now pointed down in the plane. That causes my H that's out of the plane to become an H that's behind the plane, pointed up, and my Cl that's behind the plane to come out of the plane, also pointed up. There was a hydrogen here all along. It's still there. This orientation, this conformation, makes it easier to see the mirror plane within that molecule. So a meso compound is sort of like, I think of as sort of like a tug of war. Remember, chiral compounds are optically active. A meso compound has one side that's saying, I want to rotate the light this direction. The other side is saying, I want to rotate the light the opposite direction. In the end, they completely cancel each other out, and the light doesn't get rotated at all. Meso compounds are optically inactive, which also means they're achiral. Meso compounds do not rotate plane polarized light. Enantiomers do, meso compounds do not. Meso compounds do not have an enantiomer because meso compounds have superimposable mirror images. I just threw out so much jargon at you, but I think you followed along, didn't you? Well, I hope so. Let's finish out this problem by giving the relationship between all isomers, and then we'll continue discussing meso compounds momentarily. So A and B are enantiomers. A and C, same at some, different at some, diastereomers. B and C, same at some, different at others, diastereomers. Meso compounds do not have enantiomers, but they do and can have diastereomers. Okay. So there's my definition again. We said mesos are achiral. Yeah, that's a thing. This talks about a center of symmetry. Well, here's the definition of what a center of symmetry is. I can feel good about myself for saying that at least once. There we go. Here are two compounds. Are these compounds meso? They have a mirror image. You could definitely chop the middle. It's real hard to draw where you should cut these things, but you could chop that thing through the middle. You're cutting through the hydrogen, through this carbon, that carbon, the hydrogen, the bromine. You're cutting the middle of that compound. You could definitely find a mirror plane in that molecule, and this one as well, cutting through the same plane. But neither of these is chiral, and neither is a meso. What? Mesos are so confusing. Yep, a meso compound must have at least two asymmetric carbons. These guys do not have asymmetric carbons. This is a stereocenter that is not an asymmetric carbon. Oh, so many words. What about this molecule? Does this molecule have a mirror plane through the middle there? Nope, because hydrogen and methyl would have to match, and they don't match. That compound, this cis isomer down here, does it have a mirror plane? Yep. There's a mirror plane down the middle of that compound. Methyl reflects to methyl, hydrogen to hydrogen. So is this a meso? Uh-huh. Is this a meso? Uh-uh. Both of them have asymmetric carbons, but this cis molecule has asymmetric carbons and a mirror plane. It's meso. This trans has asymmetric carbons, no mirror plane, not meso. Yeah? Meso's confusing, but we can get it. I believe in us. This is cholesterol. Cholesterol has a number of stereocenters, a number of asymmetric carbons. How many stereocenters do you find in cholesterol? There are 8 stereocenters in cholesterol. I really think you should work on picking these out on your own. But 1, 2, 3, 4, 5, 6, 7, 8. 8 stereocenters in cholesterol. Did you recognize all of those as asymmetric carbons? Maybe not. We need to get good at tracing down a molecule, tracing like from here, tracing down the line to see if those branches are identical or if they are different. This molecule where my laser is has 4 carbons connected to it. A lot of students would say that's not 4 different groups because 4 carbons, it's carbon. This over here is a CH2. This up there is a CH3. This to my left, to its left, that's the right, dadgummit. To its right is a CH, and down at the bottom is a C with no H's. I did not repeat myself. Those are 4 different groups. So if you follow the chain long enough, far enough, all 8 of those highlighted stereocenters are asymmetric carbons. All 8 of those have 4 different groups attached. You'll get some practice on big molecules in your homework. So if there's 8 stereocenters, how many possible stereoisomers are there? 256. Yeah. This is the framework for cholesterol. I already said that. But really, cholesterol has to have certain orientation of dashes and wedges to be considered cholesterol. Of the 256 possible options of dashes and wedges here, possible combinations of dashes and wedges here, cholesterol exists as one of them, and our body synthesizes only that stereoisomer. I think that's pretty cool. There are 255 options that our body does not synthesize. It synthesizes 1. Okay, so besides recognizing asymmetric carbons in cholesterol and knowing that stereochemistry and shapes of molecules is important for pharmaceuticals, what more am I going to have to know about it for organic chemistry and to do well? We are all about reactions. Reactions of stuff that we will do often have an asymmetric carbon in them, and we need to know if the reaction that we're going to do affects that asymmetric carbon or not. In this reaction, you don't know how, you don't know why, but what has happened is your chlorine got displaced and OH took the place of the chlorine. That's what happened in this reaction. We will worry about how and why later, aka test 4. But for now, I want to point out that that's what happened. Did the reaction happen at this asymmetric carbon? No. Okay? In this reaction, what has happened is my alkene was converted to an alkane. This is a hydrogenation. We'll talk about that one later as well, aka test 3. But my alkene turned into an alkane. Did the reaction happen at this asymmetric carbon? No. When the reaction does not happen at the asymmetric carbon, the reagent, that means this thing, and the product, the reactant and the product, have the same relative configuration. Relative. What that means is H was pointed back, H stays back. Methyl's pointed forward, methyl stays forward. Ethyl in the plane over there, ethyl in the plane over there. This branch that got substituted up in the plane, this branch that got substituted up in the plane. The same relative configuration. They don't switch neighbors when you don't do the reaction at the asymmetric carbon. Does it mean that the absolute configuration stays the same? Not necessarily. Well, let's check absolute configurations on these examples. So this top one, highest priority, I should make you walk through it, but I'm going to tell you, it's that branch. and then the ethyl, and then the methyl, and then the hydrogen. 1 to 2 to 3, it's S. Highest priority, second priority, third and fourth. You really need to practice this a lot. 1 to 2 to 3, it's S. Okay. Highest priority. 1 to 2 to 3, it's S. Highest priority. Interesting. 1 to 2 to 3, it's R. What? Relative configuration says that your stuff stays in the same relative position, but the absolute configuration may stay the same or it may change. In the top example, it stayed the same. In the big picture view, why did the top stay the same? Because my priorities stayed in the same spots. In the second example, my priority was 1 alkene, 2 propyl, and it became 1 propyl, 2 where the alkene was. So my priorities shifted in the product on number 2, so my stereocenter, my absolute configuration, changed in response. So don't always say retention of configuration means this or inversion of configuration means that. It depends on whether you're talking about relative or absolute configuration. We'll walk through this example as well. Oh, I should really make sure that you're getting on the priorities, but I'm going to give it to you anyway, as much as it pains me. Here are my priorities around glyceraldehyde. This is a Fisher projection, remember. That means bow tie across the middle. That means this is really R glyceraldehyde. That means this is R glyceric acid. So this one is R and R in both cases. So why do I point this out on the slide that says this happened with retention of configuration? Well, you would probably think, of course it did. R and R, retention of configuration. No, it means the relative positioning of the groups around the asymmetric carbon stayed the same. But I want to point out one other thing here. This little plus and this little minus. What does that mean? Plus means rotates plane polarized light clockwise. Minus means rotates plane polarized light counterclockwise. A lot of times students think there's an association with R and plus, or S and negative, or the opposite. No. The plus minus, which direction light gets rotated, is very dependent on the molecule, and it is not something you will be able to predict. It's all experimental. Put it in a polarimeter and see what happens to it. It just so happens that R, glyceraldehyde, rotates clockwise, while R, glyceric acid, rotates counterclockwise. Rotates light counterclockwise. The clockwise counterclockwise of my RS does not relate to the rotation of plane polarized light. Okay. We now interrupt your regularly scheduled program to talk about the stereochemistry of biological molecules. Carbohydrates, they're a big deal in biology, big deal in biochemistry. These are carbohydrates. You may have noticed that glyceraldehyde is a carbohydrate. That last slide talked about glyceraldehyde. Carbohydrates are almost always drawn when they're in their open chain form. Let me put that little addendum in there. When they're in their open chain form, they're almost always drawn in Fisher projections like this. You should look up Fisher, the scientist. I'm having trouble remembering his first name right this minute. Total brain fart. But you should look him up. He did a lot of work with carbohydrates. A lot of cool stuff. So this is a Fisher projection of glyceraldehyde. Why would I call it D-glyceraldehyde and L-glyceraldehyde? Because I've just been on this rant about R and S, and then you throw up something about D and L. Well, in a Fisher projection, the standard way a Fisher projection is presented is having the carbonyl carbon up top. That's the C-double-O carbon, carbonyl carbon up top. There's always a CH2OH on the bottom of your carbonyl, on the bottom of your carbohydrate. And then across the middle are a bunch of bonds with H's and OH's in a standard carbohydrate. If that OH is on the left, we would call this L-glyceraldehyde. If that OH is on the right, we would call it D-glyceraldehyde. D and L are stereochemistry terms, but they're really not universally applicable, or they've become a little bit outdated outside the realm of carbohydrates and amino acids. We'll look at amino acids in one moment. Interestingly, most carbohydrates found in nature are D configurations. If you've ever looked in a biochem book, you might see D-glucose, D-ribose, D-fructose. D is the configuration of most natural carbohydrates. Cool. Whoops. Amino acids. They have a carbonyl carbon as well, a C-double-bond-O carbon also. If you draw an amino acid with the carbonyl carbon at the top, the carboxyl carbon at the top, the side chain of the amino acid goes down below, and the amine goes across the horizontal in a Fisher projection. You guessed it. If the amine is on the left, this is an L amino acid. If it's on the right, it's a D amino acid. Remember the carbohydrates? Most sugars are Ds. Turns out most amino acids are Ls. That's kind of cool. Weird. Interesting. Yeah, all those things. That's enough. I'm done.